शेयर कर दो, शेयर फुल स्क्रीन कर दो, शेयर फुल स्क्रीन कर दो, शेयर फुल स्क्रीन। तो शेयरिंग बंद करेगा, मैं स्टॉप कर, आप कर दो शेयर। हाँ शेयर, हाँ फुल स्क्रीन शेयर करते हैं, फुल स्क्रीन शेयर करते हैं, स्टॉप स्टॉप शेयर कर दो, सही। अब इसके बाहर जाओ, तो बाहर स्टॉप कर दो। पे दिख रहा होगा ना, शेयर हो गया ना, तो एक बार पूछ लो इंस्टीट्यूट। वो इतनी दिखता है ना, इसको कट करोगे, इसको कट करोगे, नेक्स्ट में है ना ऊपर। हाँ चलो तो इसका हाइट प्रेजेंट कहाँ पे, स्क्रीन पे दिखता है, राइट इसको छोटा होगा। चलो स्टार्ट करते हैं, रेस्पॉन्स ठीक है, इसे पूरा दिख रहा है ना, हाँ ठीक है, ओके। यहाँ से स्टार्ट कर दो, हाँ इसे पूछ लो उधर विजिबल है ना, तो स्टूडेंट हाँ ठीक है, कोई नहीं, इसे पूछ लो, क्विकली स्टार्ट करना। इस शेयर स्क्रीन विजिबल, इस स्क्रीन इज विजिबल for the online participant.
Yeah, it's visible.
Okay, thank you. Okay, now I am starting. I would like to take this opportunity as my privilege to introduce our keynote speaker, Professor Bilas Pachori. Bilas Pachori received the Bachelor of Engineering degree with honors in Electronics and Communication Engineering from RGPV Bhopal in 2001. The MTech and PhD degree in Electrical Engineering from IIT Kanpur, India in 2003 and 2008 respectively. Before joining the IIT Indore, he was the postdoctoral fellow at the Charles Darnley Institute, University of Technology of Troyes, France, and the assistant professor at the Communication Research Center, International Institute of Information Technology, Hyderabad from 2008 to 2009. He was an assistant professor 2009 to 2013, an associate professor 2013 to 2017 at the Department of Electrical Engineering, IIT Indore, where he has been the professor since 2017. He is also an associated with the Center of Advanced Electronics in IIT Indore. His research interest includes signal and image processing, biomedical signal processing, non-stationary signal processing, speech and signal processing, brain-computer interfacing, machine learning, and artificial intelligence and Internet of Things in healthcare department. He is an associate editor of the electronics letter IEEE Transaction on Neural Network and Rehabilitation Engineering and Biomedical Signal Processing and Control, and an editor of IETE Technical Review Journal. He is also the fellow of IETE, IEI, and IET. He has 297 publications, which includes the 183 general article, conference 78 conference paper, 10 books is there, and 26 book chapter is there. He has also the 8 patent, including the 1 Australian patent that is granted and 7 Indian patent that is published. His publication has been cited approximately 15,000 times with H index of 65 according to the Google Scholar. This was just a brief description about his tremendous work experience. Now I would like to invite Professor Rambilas Pachori sir to start his lecture. Sir, please.
Yeah, thank you very much for nice introduction and good morning everyone. So today's talk is on Fourier Bessel series expansion and its applications in signal processing. So for the last 15 years, our group has done some work actually like theoretical framework for Fourier Bessel series expansion, which helps actually to use them these frameworks in biomedical signal processing. So in this talk, we will see what is actually Fourier Bessel series expansion and how it is better than Fourier transform and what are the special features of this expansion that actually that can motivate you to apply it in the healthcare applications together with machine learning. Signal processing can give you actually a nice set of features which can be helpful for identifying the disease and this Fourier Bessel series expansion can be used as a domain, new domain, and where you can develop a lot of algorithms. So it is actually it will give you a platform where a lot of biomedical signal processing can be algorithms can be developed and can be tried together with machine learning. So with this background, let us start this talk. So this is the overview of this presentation. So first we will see introduction, and after that, we'll see Fourier transform, that is well known, then Fourier Bessel series expansion and its various applications, then will see conclusions and references that is actually stock is based on that, that you can go through these references in order to understand these concepts in better way. So transform, similar to like machine learning that you have seen, inaugural part of this workshop, it is everywhere. These days, it is very difficult to find any area of science and technology where you will not find use of machine learning. Because everybody wants to have automation in life, in automation in all areas. Similarly, transforms are also actually, it is very difficult to find any area of science and technology where signal transforms are not there. You will find signals everywhere, like everywhere these days, actually, even human body itself is a collection of signals. Similarly, in all areas, chemistry, physics, you will find use of signal transform. And in simple way, this transform can be defined as a bridge between two domains. So like for time domain and frequency domain is like our electronics and communication domain. We understand these two domains very nicely. And this transform, we can go from one domain to other domain and we can come back other domain to actual domain. So this why we go at other domain, because it helps us to actually find out main lot of information, help us to solve the many problems, and these are the major actually reasons where actually transform is useful. So the first one is actually transform provides certain information about the original function or signal. So like if you transform the signal, then actually you will find out what are the frequencies present the signal, which frequency is the major frequency, which frequency is the minor frequency, which frequency is corresponding to, for example, murmurs in the heart sound, which frequency is like fundamental heart sound. So all these kind of actually different information can be obtained using transformation. And transform help us to solve the differential equation. So like in actually signal processing, we use mathematical models to represent the system. And we use actually differential equation is one of the model where the systems and signals, they are actually associated. And if you have a low order differential equation, then you can use simple mathematical books that you see, mathematics books, methods, manual methods can be tried to solve the differential equation. But when you have complicated system and your differential equation is having high order, then actually you have to go for some mathematical, like some algorithm kind of method. Or transform help us to solve such kind of differential equation, and then you can understand actually systems and signals. So in signal processing, signals and systems actually they are associated to each other. Without system, we cannot define signals, and without signals, we cannot define systems. So, like if you are solving the system, indirectly you are solving the signals, and when you are analyzing the signals, indirectly you are understanding the system. So they are actually interdependent on each other. So this transform can help us to solve these differential equations where they are useful to understand the signal and system. And the transform can provide data compression, and storage may require less memory. So like in transform, we use basis functions, and basis functions, if you somehow you are able to select them according to the structure of the signal, the requirement of coefficient will be less. For example, when we go to restaurant, we actually there are many spoons are available, but according to food, we select the spoon. For example, if you want to noodles, then we use fork because your food is discontinuous, your spoon is also discontinuous. So nicely you can handle such kind of food with a similar kind of spoon. Similarly, in signal processing, actually we want to have such basis functions which are similar to the structure of the signal. So in that way, if you select the basis function, then requirement of coefficient will be less and compression can be. A last advantage actually, some operation may be easier to apply in transform domain. So for example, like convolution operation in a linear time domain system, where we assume that system is causal. So if you want to implement this convolution in time in transform domain, so just you determine the Fourier spectra of the input signal and system and multiply, and after that take inverse Fourier transform and come back in actual domain. This is also one of the implementing convolution, but in that way, you don't need to assume anything depends on the time. So in signal processing, actually, there are three independent forces: time, frequency, scale. Whatever is happening in this world, it has connection with time. Whatever we listen, it has connection with frequency, and whatever we see, it has connection with scale. And here we see actually you are going in such a domain, there is no time. So this is the beauty of analysis. Like without depending on time, you can do entire process. So that actually transform domain analysis takes you in such a domain, there is no time. So that actually help us to solve many problems without depending on the time. Whatever is actually happening in this world, directly, indirectly, everything is connected with time. We say this person is poor person, this person is rich person. Person is not poor, person is not rich. Person is poor due to time. Person is rich due to time. And this point of time he is rich. We don't know future. So this everything actually directly, indirectly connected with that. Two persons are talking on phone. I don't know what they are talking, but I can guarantee you they are talking about time. Everything has connection with time. Time is the actually important part in life. Nothing is stronger than time. So this actually in 1807, this Joseph Fourier, he represented actually a signal in terms of sinusoidal fluxes. And this Fourier actually is a very interesting story that also I would like to share with you. Fourier actually was from France, and he was very poor. His father was tailor by profession. And when he was 4 years old, his parents died, and Fourier was actually not from noble birth. Noble birth, like in France, sometimes you don't have actually information about the parents. Parents are not known. So he was not, so that society did not allow him to go to school. Then actually he used to, most of the time he studied himself, and he used to work in hostel. In old time there was no electricity like today we have. Students used to use candles for study purpose, and after studying they used many part of the candle they used to throw outside. And this Fourier actually used to collect these small pieces of the candles, and then used to make a big candle. At night when everybody was sleeping, Fourier used to study. And this Fourier actually he joined French army, and he was physically strong. Then actually from the French army he got an opportunity to come to École Polytechnique. École is like a school in French. École is French word. It means school. And where actually he was a physics background, and he was working on the prism and then he observed that this prism can decompose white light into 7 colors. Then he got idea, if this white light can be decomposed into simple component, simple color, then why we cannot decompose this complicated signal in terms of simple signal. So that simple signal sinusoidal function. And the same Fourier actually became first or founding director of the École Polytechnique, and he also became scientific advisor of Napoleon. Then people asked him, earlier you were son of Taylor, now you are scientific advisor of Napoleon, how do you feel? Then Fourier replied, I am Sam Fourier, this is just a matter of time. So Fourier understood time in such a manner. That is actually, so he represented signal in terms of such functions which are periodic with respect to time. So that is, time is actually very, very important. And I ask my students in the class, which city is the best city in the world? They say New York, Paris. So same question I will ask you, which city is the best city in the world? Some students say Indore. Which city is the best city in the world? I asked this question in Italy last 1 month before I went. They say London. So that is simplicity. If you are simple, then you are best in the world. That actually Fourier understood, and he represented this complicated signal in terms of simple functions. And simple functions nicely you can define features. So these are one of the actually important requirement of the biomedical signal processing, where we can decompose this complicated signal in terms of simple signals, and there nicely you can define the features. That we will see in this talk. You will see various domains where you have simple functions, and then you can explore basis functions, explore the basis functions, building blocks, or non-functions or simple functions for defining the features. So according to Fourier, any complicated signal actually can be represented in terms of sinusoidal functions. And this was proposed by Fourier in 1807. And he says all periodic functions can be represented by the weighted sum of trigonometric functions. Then his student Dirichlet, actually, after some time, he concluded that not all. Dirichlet was the student of Fourier. So he says all functions can be represented by the Fourier transform when you satisfy a Dirichlet condition. So, and this work was, Fourier work was submitted for publication. These 3 reviewers were there, Lagrange, Legendre, and Laplace. Legendre is known for Legendre polynomials. Lagrange is known for Lagrange multiplier, and Laplace was the teacher of the Fourier. And Laplace transform and Fourier transform, which one is better? Laplace transform is better. So old time teachers used to be more general, not like today. Students may be better than teachers. So old time teachers used to know more. Like even Fourier transform came later, Laplace transform was earlier, but Laplace transform more general than Fourier transform. Even Fourier transform is a special case of the Laplace. So these actually 3 persons, Lagrange, Legendre, and Laplace, they have some concern with the Fourier work. These are the concerns are like in real life, most of the signals are actually aperiodic. It is difficult to find any signal periodic except time. So, and Fourier was using the periodic basis functions to represent them. So aperiodic signals you are representing in terms of periodic functions. And another concern was real life signals are real. And Fourier was using such kind of basis functions, they are actually complex. So real signals you are representing in terms of complex. And third concern was actually there is no negative time and negative frequency. And this Fourier was using such kind of basis functions due to mathematical representation. This negative time and negative frequency was coming into picture. So that was actually, there is no time cannot be negative, frequency cannot be negative. But due to mathematical model, that problem was coming. So these actually, due to these reasons, these 3 professors, they rejected his work. And after 15 years, they understood beauty of the Fourier transform, Fourier method. They say Fourier is actually thinking more generally. So like he's representing signal in complex way. So real space, real signals can be considered as a subset of complex plane. So in that way, after 15 years, 1822, Fourier work was finally published after 2-3 years. That Fourier died, and up to 143 years, there was no significant work in the signal processing area. In 1965, Scully and Tukey, they now people started using machines, computers, and they wanted to use machines to implement signal processing. So then that was the motivation for developing fast Fourier transform. Then actually how to compute Fourier transform using machines in efficient manner with low computational complexity. Then this FFT was born in 1965 to solve the Fourier transform using machines. So Fourier transform here you can see in this complicated signal can be represented in terms of simple signals. This we call basis functions, sinusoidal functions. And Fourier transform is like a bridge between time domain and frequency domain. And there are two expressions. First one is the analysis, second one is synthesis. So analysis part you can see we are integrating signal from in time domain from minus infinite to plus infinite. So there is no time in the frequency domain. In the synthesis part you can see we are integrating frequency from minus infinite to plus infinite. So there is no frequency in the time domain. So when you are in analysis, you are doing analysis, you have frequency domain. When you are doing synthesis, you have time domain. So there is no frequency domain. Time domain and frequency domain both are mutually exclusive. And this is one example. Here you can time domain 3 sinusoidal functions, 5 Hz, 25 Hz, and 50 Hz. And when you apply frequency domain, you apply Fourier transform, and you have peak at that frequency 5 Hz, 25 Hz, and 50 Hz. So it tells us what are the frequencies present in the signal. So actually what we are doing, we are designing basis function from our side and we are matching with the signal. And that particular basis function is actually showing more similarity, then corresponding that frequency coefficient will become high. Otherwise it will be 0. So in that way, this Fourier transform measures the similarity between the basis function and the signal. Now, this Fourier transform is well known. All of you have studied in your BTech time, and so there are like it's now actually we see some shortcomings in this world. Everything, whatever method, any method, not perfect. Anything in this world has two sides. One advantage, then also same time it also has disadvantage. You will not find anything in this world which has all advantages only. So we have both parts. So this Fourier transform has a lot of advantages, but also has some shortcomings also. It is suitable for stationary signals. So actually, in the real life, signals are non-stationary. Non-stationary means we use mathematical models to represent the signal. If any of the parameter is changing with time, then we call them non-stationary signal. So actually, it changes with time. And it requires window function in order to obtain spectrum of the signal. So when you obtain the Fourier transform, then actually there are spectral leakages due to finite without using any window. It's like rectangular window version. So use Fourier transform of rectangular the sinc function and it's convolved in frequency domain. So due to that, there is actually spectrum leakages, and that's for in order to reduce this spectral leakage, we use window function. And this Fourier transform represents real signal in terms of complex exponential functions. And it requires representation of real signals in terms of positive and negative frequency. The basis functions which we use in Fourier transform, they are periodic in nature and do not converge because they are like periodic functions. And the basis functions do not include modulations in the representation. So like bandwidth actually of the signal depends on the amplitude modulation and frequency modulation part of the signal. Since the sinusoidal functions don't provide any kind of modulation, so bandwidth theoretically is 0. The spectrum based on the Fourier transform can provide frequency points equal to the half of the signal length, because due to complex conjugate symmetry, only half spectrum is useful, other half is repeated. So that actually, if you have n number of points in the time domain, capital N number of points, then you will have capital N by 2 frequency points. So luckily, there is another actually transform, that is Fourier-Bessel series expansion, that can be used as an alternate of the Fourier transform. That was actually in '94. It was tried by the Jim Schroeder, in signal processing based on the simulation. And K. Gopalan, Professor K. Gopalan, he was with University of Purdue. He also actually tried this first order Bessel functions, and they all were only it was just like simulation. These two persons, and third one is actually during my PhD time, I tried to develop a theory for this how to now here we can see its advantage same point to point. So, like in case of Fourier Bessel series expansion, it does not require use of window function in order to obtain spectrum of the signal because these Bessel functions they decay with time. So already window is inherent in that and it represents real signal in terms of real Bessel basis functions, and it provides representation of real signals in terms of positive frequencies. There is no negative frequency, and the basis functions used in FBSE, they are aperiodic and in nature and converge with time. So the damped after some time becomes zero. And the basis functions include amplitude modulation in the representation, and the spectrum based on the FBSE provides frequency points equal to the signal length. So this resolution is actually double compared to the Fourier. And there is zero padding, but zero padding doesn't improve the resolution. It is just like readability. So just looking at different scales. So that like this is interpolated version of the spectrum. But this is in this case, you will have double frequency components, double frequency points. So resolution is double. Now, how these Bessel functions have come? So now we'll see actually this is a mathematical background of these Bessel functions. So these Bessel functions are the solution of linear second order differential equation. So the first differential equation you see, then it's a solution y equal to a jvx plus b by bx. So this a and b are arbitrary constants, and jvx and by bx are the Bessel functions of the first kind order v, and the Bessel functions of second kind. So this first one jvx, they are actually useful to represent the signal. They have orthogonality and similar like sine cosine functions. We can use them, and but in the literature till this point, only zero order and first order of first kind Bessel functions have been studied. Nobody has tried more than that. So that, but they are all are orthogonal. So there are a lot of actually research can be done in this direction, but only we have seen the zero order and first order of first kind Bessel functions are useful for signal representation. So here actually this is dx. So x jv alpha x jv beta x dx equals to 0 integration that is missing. So this actually these two roots alpha and beta they follow orthogonality principle. So if you have Bessel functions corresponding to these two roots, and then you integrate. So this here is weighting factor is x. So this orthogonality is different than the Fourier domain. So with the weighting factor x, you can define orthogonality, and alpha and beta are the two roots. And here you can see these are two zero order and one order of first kind of Bessel functions. These are examples. So this zero order, it looks like damped cosine functions, and second one looks like damped sine basis functions. Still, we actually the one of the open problem is what is the damping factor? What is the relation between the damping factor and the bandwidth? So like each Bessel function has damping, and it represents some bandwidth. But what is the how much bandwidth represented by the damping factor? How to estimate the damping, and how to determine that bandwidth? So that still it is not done, and we are trying to work on that. So these kind of actually these two different representations can be used as an alternate of the Fourier transform, and that actually have been explained in the literature, and we have also used them, developed some processing frameworks, and then you can try them for healthcare applications. So here you can see this in the first part synthesis equations for zero order and first order. So when zero order, then you are using zero order Bessel functions, and first order, then you are using first order Bessel functions. And since analysis equations are given by the this bottom one, AK and BK. AK is the like coefficient for zero order for the Bessel series expansion, and BK is the order of these are the coefficients for zero like one order FBS. And this how to determine these actually roots. And now actually in MATLAB direct command is there, but when actually I tried this during my MTech PhD time, there was no command. So we have written like interruption method, Taylor series we use for Bessel function. Then we Taylor series expansion, this Bessel function can be written this way. Then by using interruption method, we can determine the roots. But now this directly, this command is available in the MATLAB. You just the roots of the Bessel function search, and you can just give the Bessel function, it will give the roots. This is actually the relation between order and frequency. So it was actually 94, this 94, 93 was on research paper, and it was written, it is actually impossible like to determine relation between frequency and order. And actually when I took this problem, then I wanted to have relation between frequency and order. Once you have this relation, then nicely you can use as a spectrum. And it took me 2.5 years. I went through many papers, many books. Then in the one integration I got in this derivation, and that was computed over finite interval. But for infinite interval, its solution was there in the literature. But for finite integration, this was not available. And actually, one book I got that Bessel functions for engineers, where the method was given. Actually, that method actually I employed here, and then this problem was solved, and I was able to show the relation between order and frequency. So if you have beta k, that the kth root of the Bessel function, this is connected with the fk in hertz, and L is the size of the window. So if you have any signal, its the size of the signal is L samples or L seconds, and it's then this relation can be used to determine the frequency. So you use Bessel functions for your Bessel series expansion, and then whatever order it is becoming higher peak, that order you can convert into frequency. And so that order actually can be converted into frequency, and then we can use this Fourier Bessel series expansion as an alternate of the Fourier transform. That is actually provides you spectrum of the signal. One actually good thing is that like in Fourier transform, you are getting complex spectrum. So it has two spectrum. One is magnitude and second one is phase. Here you have only real spectrum. There is no complex. So this is because basis functions are real, signal is real, so coefficients are also real. But it is not explored too much. But for me, it is very useful decomposition. Last 15 years, I am working on this. I am finding it very useful. I want all of you try this decomposition in your work. We can provide you MATLAB code also, and some codes are publicly available also. So now this actually in last 15 years we have explored this Fourier Bessel series expansion for various applications. You'll find many a couple of papers actually from our group, and these are the some of the algorithm that is selected. And just to explain this work, that is the new technique to reduce cost terms in Wigner distribution, and EEG signal analysis using FB expansion, Fourier Bessel series expansion, second order linear TBR process. So EEG actually this time varying autoregressive model, it was proposed by the Grenier in 1983. And this model works for all kind of signals, but when you apply this on brain data, brain signal, EEG signal, it doesn't work. So based on the Fourier Bessel series expansion, we segmented it and we found that AMFM kind of nature, amplitude and frequency modulated nature of that segment. And then you use second order TBR model, time varying autoregressive, that we'll see. And then we have also proposed discrimination between ictal and seizure free signals using empirical mode decomposition. based on the mean frequency proposed by the Fourier-Bessel series expansion. In the inaugural talk, there was mentioning Professor Ingle, NTU Singapore, you worked on epileptic seizure detection. So this epileptic seizure itself is the word that is used by the doctors for the epileptic seizure. So that also can be discrimination can be done. And then analysis of multi-component amplitude and frequency motor signal using FB desa method. So this was actually P. Maragos is one of the well-known person in speech processing, and he modeled signal based on the AM/FM components. So they use Gabor filtering to separate out these components. And here actually we have suggested use of Fourier-Bessel series expansion. And now this signal processing, people are using adaptive decomposition like empirical mode decomposition, where we are getting AM/FM components. So earlier they used to represent by the AM/FM model, then they used to separate out. Now we decompose, then we use AM model. So like prepaid mobile and postpaid mobile. So sometimes we pay the money, then we call. Sometimes we call and later we pay the money. So similar way, this decomposition modeling will also work. And then Fourier-Bessel series expansion based empirical Wavelet transform for analysis of non-static signal that we have defined. And epileptic seizure identification using entropy of FBSE based EEG rhythms. So like rhythms generally literature, they have wavelet transform, filter banks, different methods to separate out rhythms, and we have suggested use of Fourier-Bessel series expansion for separate out rhythms. Then these rhythms can be used for the epileptic seizure identification. And after that, classification of focal EEG signals using FBSE based flexible time frequency coverage wavelet transform. So this was defined based on the Fourier transform, and we have suggested use of FBSE for this flexible time frequency coverage wavelet transform. So these two epilepsy, that seizure, epileptic seizure, that is generalized epilepsy, it can be anywhere in the brain. And this focal epilepsy, that last one you can see focal, that is actually a little bit serious. 80% cases is drug resistance epilepsy. Drugs doesn't work, medicines doesn't work. And there's a specific region in the brain from where this seizure originates. So you have to identify the region, then so surgery can be done. So signal processing machine learning techniques find actually very useful application to identify accurately that region, and that can be removed. So that is actually for that intracranial EEG signal. So some surgery is required to record the signals with the high signal to noise ratio. In other cases, generalized seizure, you can record from the surface of the brain, the surface EEG recording. So one by one, actually, we will see these developed frameworks. So the first one, this a new technique to reduce problems of the Wigner distribution. So like in signal processing, actually, for non-static signal analysis, this time domain and frequency domain, individually they are not sufficient. We actually need to combine them. That is known as joint time frequency analysis to have meaningful time frequency, meaningful representation of the non-static signal. So there is a very oldest technique, that is a classical technique of time frequency analysis. There time and frequency domain both are present together, and that is known as that is Wigner-Wiley distribution. And Wigner was from physics background, Wiley was from communication, and they together they worked, and they developed signal processing algorithm that can be used for the non-static signal processing. So that is Wigner also got Nobel Prize for such kind of work. So here you can see the first one, the Wigner-Wiley distribution is defined in time domain. So that is actually can be considered as a standard form of the Wiener-Khinchin theorem. So like Fourier transform of the time-varying autocorrelation function. So that will give you the power spectral density, but time-varying power spectral density. Second one also can be considered as a frequency domain version of that. So in that way, actually, you can get the time-varying power spectral density in the both domains. So this representation theoretically gives you infinite resolution in both domains. So because in first I am taking time from minus infinite to plus infinite. Second one I am taking frequency for minus infinite. So when you have in time spread is more, then frequency spread is less. Resolution. Resolution, focus, concentration, that is proportional to 1 upon spread, the area. the spread that is covering. So old time people used to use a small mirror to see the face, and these days people use dressing table to see the face. Which one has good resolution? Small mirror. Because old time people were wise because it has good resolution. If they want to put tika, they will use small mirror, not dressing. If more area is less resolution, low concentration. If you stay in 2 BHK house, you have good resolution, good focus. If you stay in 4 BHK house, poor resolution, poor focus. You can play football also in the house. So always actually signal according to signal processing, if you are associated with the less things, then you have good resolution. So like this, you are in one domain you are going infinite, then other domain you have very good because your spread is very less. So ideally, theoretically, this Wigner-Valley distribution has infinite resolution in both domains. And when you actually, this is, you can see in the previous definition, this is multiplying, two signals are flipping and multiplying. So due to that, is nonlinearity generated. And when your signal is multi-component, so like signal is a sum of m components, then you can see the Wigner-Valley distribution has sum of auto terms, auto WBDs, and cross components. So these cross components are actually very serious, and they create problem for the interpretation of the WBDs. And you will see some examples. So this is the proposed framework by us, and we have multi-component signal. Then the first time in the literature, actually we propose the filtering using Fourier-Bessel series expansion. That's like signal separation. So multi-component, this mono-component signal can be separated using Fourier-Bessel. So you go in Fourier-Bessel domain where you can find these components are well separated, and you can take different range, and you can find out the mono components. Now, in last 15 years, this was that. Now you can see actually the different adaptive methods are coming in the picture, and they are using adaptive signal processing to separate that. Also, we have modified using this Fourier-Bessel. So this talk we will see. So once this multi-component separated mono-component form, then we apply Wigner-Valley distribution to each component, and then we sum all Wigner-Valley distribution. In that way, we can get the cross-term free Wigner-Valley distribution. And WBD active mono-component signal, sometimes the signal also can have negative frequency and positive frequency. So in order to have only one kind of frequency, we have used analytic signal representation, that is often used Hilbert transform, before computing WBD. So instead of mono-component signal, we have converted into analytic form of the mono-component. So in that way, you can have Wigner-Valley distribution of the signal, and that is cross-term free. So we'll see some examples. This is actually one example. It is a mixture of two chirp signals. Chirp is like frequency is decreasing, and one other chirp frequency is increasing. Chirp word has come from the word sound. That is actually a lot of signal processing you will see in the rural areas. Words also use a lot of signal processing. That is one word is actually in rural areas known as alarming word. Like in rural, urban areas, you have alarm, but in villages, nature gives alarm. So some words are there. Anything they see abnormal, they start ringing. That I don't know what is the name of that word, but in rural areas we call it galgalia. Galgalia means gala. Thought is like resonances are there, like, and that word will generate sound till that some abnormality. For example, a snake is there. Continuously, that word will make sound till that snake is gone. So we have actually such kind of word. Like another word is bat. Bat is based on the signals sound. Actually, it generates the signal and sends, and based on the received signal, we perform that in the direction. In that concept, we use radar and sonar. And the chirp signals are commonly used in such kind of signals. And even this bat is so intelligent word, it can detect that the target is actually live or not. So that whether he should go that side or not, in order to be looking for the food. So that properties of the material also can be identified from the signal. That is actually, it's not just like even just we are just looking the signal, not looking the inside from where that is coming. That is, so even where it is sleeping. Sleeping actually, many things we can think during sleeping. Yeah. When you are just opens your eyes, then you see finite. When you your eyes, you see infinite. So somebody sleeping doesn't mean that he's not thinking. He's maybe thinking deeply, connecting with other concepts. So we have say sleeping is for everyone, not for you. So this these two chirp signals, one is actually decreasing, other one is frequency is increasing. And now you can see the Fourier Bessel series coefficients. Nicely, two clusters are there, so you can separate out. So different range of the coefficients are used to separate out these components that you can see. And then actually, in the bottom, the first one is the beginner distribution without separation. So there is cross components. So instead of two components, there are multiple components. But you see in the our proposed method, you are getting nice time frequency representation. And these you can try for biomedical signal, these concepts. Other one is actually two chirp signal. They are positive chirp, so both frequencies increasing with time. And you can see in the Fourier Bessel coefficient domain, they are actually they are well separated. And if you can find out different regions can be separated, and then you can separate out the components, and then you can determine cross terms free variability. You can see the bottom one. First one is cross terms with cross terms without separation of the components, and this is with our proposed method. And this example shows the actually signal is a mixture of two time limited and frequency limited signals. And in pixel domain, you can see now both are well separated, and separate out components using this coefficient, and then you apply the proposed approach, and you can actually get that cross term free time frequency. Otherwise, you have three components. You can see the bottom. So this is actually like BAT signal. When we have seen BAT echolocation signal, there are four components, but they are well separated in time frequency domain. So this Fourier Bessel domain, Fourier Bessel series expansion, we propose time order representation like time frequency representation spectrogram, and where we have separated the components. And after separation, we have applied actually. So these are the separated components, and using this time order representation, and then by the proposed method, you can get the vector time frequency representation without cross terms. So these actually concepts they can be tried in this medical signals for healthcare applications. After that, this 1983, this Grenier by Grenier, he's from ENST Paris, and he come up with a time varying autoregressive model. So like there are signal processing approaches. There are parametric approach, non-parametric approach. In parametric approach, all time people want you to understand the system. So like speech is represented by the parametric approach, but where we use the knowledge of vocal tract. So the system actually is represented by the model, and with that actually we used to represent the signal. So that is parametric approach, where we need a lot of information about the system from which that signal is generated. So this time varying autoregressive model, it was proposed for non-stressing signals, and it is just general form of the autoregressive model or linear prediction model, where these parameters are time varying. So this was for non-stressing signal, but it works only for few signals like speech and synthetic signals. But EEG signal is a highly non-stationary, so it was not working. So this is actually the process. We use time varying autoregressive model in the form of basis functions. Then we determine the coefficients, and then again from the coefficient we estimate the parameters, and then we reconstruct the signal, synthesize the signal. So we have proposed actually what we have observed, like you have signal EEG signal, and if you see the first case, it's spectrum, it has a lot of variations. But when you limit the signal length, then actually Fourier Bessel coefficients also showing less variation. Then we have come up with a very less length of the signal, for example, 30 samples, then we have seen 3 peaks in the spectrum. So when you have 3 peaks in the spectrum, then this is the characteristics of the amplitude and frequency modulated sinusoid. So that can be modeled by second order TVR process. So in that way, we suggested use of second order TVR model. So you segment the EEG signal, and based on the Fourier Bessel series expansion, you identify the length of the signal, which can be represented by second order TVR model. In that way, concatenation, we can represent entire signal with the help of a time varying autoregression model with low order or two. So here you can see like 3 parts: first, second, third. Actual EEG signal and reconstructed signal using this proposed approach. In that way, in the fourth one, the bottom one, you can see actual EEG signal and reconstructed. Both are showing the same actually nature. They are similar to each other. So this model actually also can be used as to represent the EEG signal. And you have seen like when you have epilepsy, then these parameters will be different. When you have depression, then these parameters will be different. So this parameter itself can be used as a set of features. So instead of going for this black box machine learning, better to try to use some features and connect these features with the level of the disease. So in that will be explainable AI, and it will be nice use for healthcare application. You please go through some of our papers where we have come up with a very nice features. Feature itself is actually can give you nice analysis. You don't need classification. So this is like you'll see the parameters: segment 1, segment 2, segment 3. So different segments, your parameters are changing. Now instead of that, you consider normal EEG signal, abnormal EEG signal. So you will have different features, and you can use them as a set of. So this actually signal processing part is now actually you can use it again, like people this data learning, machine learning, people have forgotten the signal processing. That is important part. Analysis. Interpretation is very important. If everything classification, you go to doctor will say you are not well. But you are also interested to know how much the disease is, the beginning, initial, intermediate, what level of the disease. And you say now is the beginning, you will be happy. That is the, I'd say, fine, I will be happy or well with the treatment. So say that signal processing can tell you what is the level. Correlation can be developed with the level of the disease with the parameters. That actually missing in the machine learning. Machine learning, the person who is applying machine learning, who has become machine. We have to be human. Machine is machine. Machine is actually assisting us. We should command machine. We should understand what we are doing. That is so new area. Actually, when I presented this kind of work that I am doing, our group is doing in Germany in Freie University. That group quickly said this is explainable AI because the signal processing part is signal processing. If you include in the machine learning, then it is everything is clear. What is going on? What feature you are classifying? What is the feature? What is the insight? Without that, you just CNN automatically learning and giving. So insights are not there. Interpretation is very important part. Interpretation will be only when you have analysis. And this actually, it's ictal and seizure free. Ictal means like epileptic seizures. So in brain, these neurons actually they synchronize with each other, and they generate very high electrical activity. That to do that, once you have high electrical current, then actually brain disturbs due to high current, and brain is the master of the body. Once brain is disturbed, then everything is disturbed in the body, and that is very serious disease. In rural areas, you must have seen somebody is from village, then they get epilepsy attack. They what they do? Yeah, intelligent. It's actually village people. They bring some old bananas, something that smell very strong. Yeah, smell. So that your neurons will be busy with that work. They will get some work. smelling. So the strength will be less. Otherwise, so they will give you some assignment so that the neurons will be busy with that work. So electrical current will be. Now, so rural people are very smart people. You will find many actually algorithms, many concepts in villages. That is, urban area people are following each other. They are busy in running, but in villages people find the concepts. Old time, uh, they used to predict actually the number of guests based on the crows. Suppose in the house 4 crows are coming, then they will see that 4 guests will come today. So guest in Hindi we call Atithi. Atithi means you don't know Tithi on which they will come. If you know the Tithi of the Atithi, then he's not Atithi. That is actually, it should be highly unknown. The old time actually people used to know how to manage with the Atithis without knowing Tithis. That the people are not like today. 4 persons are coming quickly. I went to shop and I brought things. Old time people used to solve the problems actually unknown problems. They don't know how many guests will come, but number of guests, whoever will come, they will actually handle that problem. That is research. If I know I called, I am coming with 4 persons and the sugar, everything, tea, everything. Maybe village there is no tea, but there will be tea for the guests. Somehow it will be arranged. That actually, that is the research. And number of crows, based on that, they are detecting number of guests. I don't know whether right or wrong, but at least probability is there. At least estimation is there, detection is there. The person in family is predicting how many guests are coming based on the crows. That is the research. If everything is known, then what is the need of research? So in villages, actually, the many things are unknown. Farmer is doing a lot of hard work, but he doesn't know after 1 month will he get money or not. And that is actually, that is required research also. We do a lot of hard work, we don't know whether we will get results or not. So that person is highly suitable for research. That is actually, that research requires such kind of teachers, where you can handle the uncertainty, you can actually deal with the uncertainty. Like labor person, he is poor, someone he is a poor person, but for research he is a rich person. Because research, whatever required, that poor person already has. So poor persons actually they are rich persons, and rich persons are poor persons for research. You'll find a lot of people they don't have background and they generate background for others. Like Fourier was not having background, but everybody is studying was Fourier. Many people will be rich that time, but nobody talks about them. So the poor people, they actually they develop the background for others. The all breakthroughs, this Ohm's law. Ohm was actually after PhD, he was not having money to pay the fees for becoming professor, so he joined the school. 8th class students used to teach, and his father actually was a locksmith. He used to make duplicate keys, and his father says, "I want you to go ahead with my business. You should also make duplicate keys." Om says, I'm interested in study this professor, all these things. He wanted to become professor. And then Om decided I should continue with what. So he told that father, he learned from father. Father is actually, if you give him lock, he will make you key. It's very good solution he is giving. So he says, by actually opening the mechanical lock, I will make key for the electrical lock, that circuit. So that with that motivation, he actually developed the electrical circuit, Ohm's law, V equals to IR. That is circuit switch. Right. So idea locksmith actually that he got idea for is everybody electrical engineering Ohm's law. So all actually all stories are like that only. This poor people actually is always poorness is for great work. This is not just for like a bad work. It's rich people, they will buy many cars, many houses, 4 houses, 5 houses. More richer, more poor, more people. You will not find any person who will say I am rich. Rich person becomes more poor, more poor. As one sleep disorders in the healthcare that actually we study in India, people are very good in sleeping. You will find a railway station also. A railway station they sleep. In farm also they can sleep. Anywhere they can sleep. But you will not find any in other countries. They are very robust. But only the people that they develop sleep disorders, they always talk about money, 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 money. If you always say money, 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 then this means your Lakshmi ji is here and you become carrier of Lakshmi. Lakshmi ji here and your entire body is the carrier of Lakshmi. And who is the carrier of Lakshmi ji? Owl. And owl is active in night. And such persons are active in night, they don't sleep and they don't allow others to sleep. Such people develop sleep disorders in India. Others people are very happily sleeping. You will not find any poor person who is going to hospital for sleep disorder. All are nicely enjoying life. Railway station will find a big queue is there. Everybody is sleeping. And that is actually sleep disorder. That also we have done some work. And that actually rapid eye movement. When we sleep, there are 6 sleep stages: awake, non-rapid eye movement, S1, S2, S3, S4, and last one rapid eye movement that we call Brahma Murta in India. That is actually responsible for the dreams, deep sleeping. And if you see, like in villages, if you tell them, I have seen the dream in night, then they will ask you, what time you have seen? In urban area, people will say, तो आते रहते हैं क्या है? Dream is not a dream. But in the villages, they will ask you, what time you have seen dream? If you have seen in the morning, then it may be serious. That is research, and literature also says the rapid eye movement. If you have seen the dream, it may be like true. Ramayana actually, Mandodari, she has seen the dream and she predicted in the dream that Ravan is going to die next 2 months, and it happened also. She conveyed this message to Ravan. So dream actually, lot of research is going on to understand the dreams, and people are actually trying to signals different reasons. Like in villages, they interpret dreams very seriously. Like in these days, we communicate with each other nicely. We talk to each other over mobiles, but whole time communication was not there. Based on the dreams in village area, people used to predict. And some girl has seen the bangles in the dream, then they used to predict that this year she is going to get married, and every entire village will start preparing for that. Some function will be there, buy new dresses, all these things. So that actually prediction is done. That is required in the research. Research needs beginning, like you said, that this already poor people have good training of the research. I just since it is started, I this EEG, I will give you of the EEG. EEG invented by the Berger in Germany. They sent, and this Berger confirmed the same thing what the sister was actually saying. So then Berger thought that my brain was communicating with the my sisters, and Berger started with the wrong assumption, but it ended with the right. So we learned from the actually process. So this EMD now this here we have actually proposed in this work. We have proposed mean frequency computation using Fourier Bessel series expansion. There is the EMD method recently empirical mode decomposition. It has been proposed in the literature, and it decomposes automatically signal in terms of amplitude and modulated frequency components, and each AMFM component narrow band, so we can use mean frequency component estimation for each narrow band signal. Then this mean frequency we have given as input to Kruskal statistical test, and based on the probability, if there is probability less than 0.05, then we call it statistically significant difference between this seizure and seizure. So here actually for that there is Hilbert-Wang transform in 1998 that was proposed. So EMD is actually part of this algorithm, and like in Fourier transform, we are representing from sine cosine function. Here is an algorithm which will decompose signal into AMFM components. So like sinusoidal pulses, their parameters, amplitude, frequency, and phase, they are allowing to change with time. So we call them AMFM functions. And this EMD method, all IMF, they satisfy two conditions. First one is number of extrema and number of zero crossing. This should be same or differ at most by one. So it condition ensure that this IMFs, intrinsic mode functions, but they are similar to sine cosine function, and the mean value of the envelope defined by the local maxima and local minima is zero. So it is like symmetric. So these IMFs, their IMF means intrinsic mode function. We have obtained from the signal itself. So that is actually symmetric, and this is simple algorithm. Take signal, determine the maxima, minima, then interpolate them, determine two and residual set is applied to these two conditions. So satisfied, then we call it IMF. Otherwise, repeat the same process. So in that way, we'll see one example. So this is like a signal that determine the maximum envelope, determine minima envelope, and determine average of these two envelopes. And this should be actually zero. The whole purpose of this. So we subtract this instantaneous average from the signal, and then we residual, and we repeat the same process again and again till this becomes zero. So here you can see now this instantaneous average between these two envelopes is becoming zero. So that is whatever IMF you get is symmetric in nature. And you can see this empirical mode decomposition of LDEV signal. So signal ED signal and decompose into simple components. So the first IMF is like a highest frequency present the data, that is also lowest scale, which gives you the detail. And last one is the lowest frequency component or largest scale. So the scale is actually very, very important, and you can have different scales, and that all the different scales can be studied, and you can determine which scale is better for your data, for your analysis. If you see the legs of the elephant, elephant looks like a tree, but elephant is not a tree. If you see the tail of the elephant, elephant looks like a snake, but elephant is not a snake. If you want to see elephant like an elephant, then you have to see a proper scale, and that scale you don't know. So similarly in biomedical data, there are many possible scales. Which scale is actually good for your information? So that actually such kind of methods gives you the different scales, and you can come up with the conclusion that which scale is better for the component. Now using in machine learning also. So one student is from BITS Hyderabad, BTech student, Dr. Rajesh, he has applied this multi-scale neural network, multi-deep learning. This scale concept is now also people are trying in machine learning. So here, this is actually our proposed expression, mathematical expression for mean frequency, and there actually this energy we have defined, and now energy is here is different, not like Fourier case. So according to the mathematical expressions or orthogonality principle, energy definition is different, and based on that we have computed mean frequency. And here you can see the first four IMFs, mean frequency is higher for the axial case, seizure, and mean frequency lower for the normal seizure free. Seizure it is lower, and seizure free it is higher. So based on that, actually, we can identify the disease analysis itself. And later, actually, we have also explored machine learning based classifiers to this automated classification. But analysis itself now actually smartphones, people are proposing tomorrow actually we'll see this biomedical imaging. So what actually people use such kind of device, this fundus image, just put the camera, it will take your fundus image, and here you will get the results. Such kind of smart actually medicines cares are coming. You don't need time, just you have such device, just show me your eyes, I will see this and see your result. Thank you. For size. So there's such kind of actually innovative frameworks are coming. So such type of analysis people are doing just quickly. You just we take your signal and EEG recording systems are not like complicated. Emotive EEG recording. It looks like just you can wear like belt, hair belt. It's these days I don't see, but old time school girls they used to wear hair belt in schools, our school, and that is just nobody will know that your signals are recorded. It looks like some belt is there, and simple wireless, and these EEG signals will come your mobile, and then you apply these algorithms nicely. Analysis can be done in real time. After actually here this we have proposed another method for AM/FM signal analysis. So like this EMD method, empirical mode decomposition that you have seen, where we are using algorithm, we are representing signal in terms of IMFs, and each IMF is AM/FM component. So this is one way, and this is another way. Their speech is also biomedical signal. Speech, Parkinson disease, lot of actually diseases can be detected from speech. And now slowly, speech people are also moving in medical applications. But analysis part is a lot of work has been done. So they are also going for vocal tag diseases, diagnosis of the diseases based on speech. So this AM/FM signal model, that actually this was the mathematical model, this one, and this we want to separate out in mono component, and then there is a discrete energy separation algorithm, which gives you the instantaneous amplitude and instantaneous frequency. And this Gabor filtering for that separation of this mono component AM/FM signal, Gabor filtering was suggested in the literature. And then you apply this DESI algorithm to determine the instantaneous frequency and instantaneous amplitude. So here actually, mathematically we have shown effect of the bandpass filtering, and whatever this time varying amplitude and time varying frequency, they are actually modified version, they are filtered version. So motivated by that, we have separated actually signals using Fourier-Bessel series expression. So AM/FM, we have developed theory. You can see here this AM/FM signal and multi-component, and based on the Bessel function, Fourier-Bessel series expansion, we have separated out and like this is a proposed model. So we have multi-component AM/FM signal, then component separation using FBSE. Then you have different components, and you apply this method, and then you have distributed frequency. This is Marago's work, and Marago's supervisor was Cager window. So that is actually live. So this is Cager, Maragos, and Maragos that actually then we have actually, and this paper took 2.5 years. So I submitted this paper at IIT Kanpur, and I went to France. I completed my postdoc, and I did my job also in IIIT Hyderabad. And after that, it was published because it was strong opposition of that concept that comes from this Maragos group. So now you have nice actually, and these in speech processing, these instantaneous amplitude, instantaneous frequency, these sets can be used as a feature set for speaker recognition. So speaker recognition done, but now we want to have actually disease recognition for healthcare based on the speech. Parkinson disease, emotions, stress, anxiety, depression can be detected from the speech signals. These days depression is very common. Our time actually nobody was knowing what is depression. In villages, nobody knows what is depression. But when I came to higher education institute for study, then people are in depression. There's some say unipolar, bipolar. In my village, I never heard what is depression word. Nobody knows what is depression. Because everybody is just doing routine. Their life is going on, and they follow each other. And in IITs, people are in depression. The students are depression. Counselor is there for counseling. In villages, actually, parents themselves are the counselors. So this is a multi-component two-stage AM signal. There are two components, and here you see this time domain representation, and here these are the Fourier-Bessel coefficients, and nicely they are well separated. You separate out these components, and we have separated using this Geber filtering also. So you can see the distortion here, and here, there. So this is the then actually reviewer says, let us don't go for Fourier-Bessel series expansion and go for infinite impulse response filter. Choose very high filter order. Then actually we use this very high order filter. So that is actually something like 100 or something, not there in the paper is mentioned. Then we have compared with this also, and then you can see this is the actually appraising of instantaneous frequency, HSC with the high order filter data and MSC with the FB data. So then also actually we are getting better result with the FB data. It is better than infinite impulse response filter. So you are very high filter design. Then this is another signal, AM/FM signal. So two component AM/FM, and you see the Fourier-Bessel series expansion coefficients. And then separated components using FBSE, separated components using Geber filter. And this is why the Maragos their contribution. So this Tager energy operator that was proposed by the Tager, by this Kazer group. And Maragos, the only group they proposed only Geber filtering, but they represented entire problem as like a good solution. So the Geber filter we replaced by this Fourier-Bessel series. And this is using our high order filter. Then we have compared this estimation and this frequency. And this is for speech. When you say A, then this is like four formats are there. So then we are separated out, and these are the amplitude frequency of these four formats. And such actually methods can be applied for speech, like based biomedical clinical healthcare. After that, recently, empirical wavelet transform has been proposed. EWT we call empirical mode decomposition. We are actually based on the maximum minimum picking time bomb. So here, empirical mode decomposition has two limitations. One is actually it has a mode mixing problem, and second one it has empirical nature. There is no mathematical theory explanation. It is empirical observed, and but it works. That here this empirical wavelet transform, that is actually empirical concept domain concept we used in the frequency domain. So we detect maximum minima in the frequency domain, and based on that we detect the boundaries, and from the boundaries we design the filters, wavelet filters. So that is why it is known as empirical wavelet transform. So now Fourier spectrum is used to segment the different regions. Instead of that, actually we have suggested use of Fourier-Bessel series expansion. So due to that, we call it Fourier-Bessel series expansion based empirical wavelet transform. So here you can see this is a this Bessel function, and this is a spectrum. It represents band of frequencies, and this is the order. Only one coefficient is sufficient to represent this Bessel function in Fourier-Bessel domain, and this is the frequency corresponding to this order. So this is our entire actually the framework. You have signal, then proposed method you determine FBSE spectrum, scale space representation of FBSE spectrum, the detection of boundaries in Fourier-Bessel domain, then filter bank corresponding to FBSE WT method, and then you have subbands, and then instead of Hilbert transform, we have suggested use of normalized Hilbert transform, and that way you have nice distance frequency, and then you can have time frequency representation, and that is actually can be used as a signature for that disease identification. So we will see some examples. So like this is the three cases where frequencies of the three component signal, they are spaced by 1 Hertz in first case, second case 2 Hertz, third case 3 years. So you see this Fourier-based method, they actually helps in the first two cases. Only it works in third case when frequencies are apart. They are spaced large, like with a large interval. And on the other hand, if you see in case of Fourier-Bessel series expansion, it is working for the second case also. So here, and then these are the filters, low pass like wavelet-based filters for the approximation and detail part. And then this you can see time frequency representation. This time A is expected for this for case 1, case 2, case 3. And this is using Hilbert-Wang transform time frequency representation. This is using time frequency dot empirical wavelet transform. This is time frequency representation using Fourier-Bessel series based expansion based empirical wavelet. So here two cases we can get better. So it is improvement of the Fourier transform based empirical wavelet. So here you get a very nice example, this epileptic seizure. So when you have epilepsy disease, then this is actually time frequency representation using Hilbert-Wang transform. But this is actually using empirical wavelet transform. This is using Fourier-Bessel series expansion based empirical wavelet transform. So when you have epilepsy, then all neurons they synchronize together, they generate very high electrical activity, and there is presence of the spikes in the data. Due to spikes, you are expecting low frequency component as well as high frequency component. So here you can see here is giving a better resolution of both components, low frequency, high frequency. So with that interpretation, we can say that our proposed method is Fourier-Bessel series expansion based empirical wavelet transform gives better interpretation or better time frequency representation for the interpretable of the disease. That is epileptic seizure nicely can be characterized. It can be used as a signature. Just use mobile and this photo one can see. You can put the boundaries. If this frequencies are coming higher than this, then its alarm will be on that person has seizure. It has large actually amplitude also seizures. One professor in NTU Singapore, he has converted this EEG signal to sound. So whenever like EEG to sound generator, whenever person has epilepsy, then the amplitude become high. Amplitude become high, then make lot of sound. This is the testing. So this modulation, so this audio signal will, and everybody will know that this person is going to have seizure. So whenever initial stage, slowly sound will increase like that. So when you go to hospital, based on the amplitude values, doctors detect this epilepsy with large amplitude and corresponding that this modulate that voice range frequency of this signal that is modulated in the audible range, and when the amplitude is large, then so that is it. That kind of concepts are actually can be designed. After that, actually, we have separated EEG rhythms. EEG rhythms are the basic rhythms. Even when this Berger defined rhythms, he talked about only Berger rhythm, we call alpha rhythm like that. And because that time people used to do only one kind of activities. That rhythm is changing with time. This was one interpretation. But now these days, at a time you can have many rhythms. So delta, theta, alpha, beta, gamma rhythms. And then actually, it's Bonn University database we have used, and we have suggested this is the framework. You have EEG signal, then we comes extraction using FBSC method. Then we extract the features. Then we perform feature ranking and classify. So it would give you healthy or seizure classes of the EEG signals. So this how to separate the rhythms. So different frequency range, we have actually determined the orders by that relation order frequency relation, and for that frequency that order from the expansion you use in the reconstruction, others you make zero. So in that way you can separate out rhythms only one step process. And then these are this is the EEG signal rhythms. This is theta, alpha, beta, gamma rhythms. And then we have weighted multi-stage live permutation entropy is computed from the obtained EEG rhythms. Then LSSM classifier is used for the classifying purpose, and all these features are not actually relevant. So we have used ranking using Bhattacharya stress algorithm, entropy, ROC, student t-test, Wilcoxon for the finding the significant features. And this actually, after that, recently, this another time frequency representation is proposed, that is flexible analytic wavelet transform. So like this wavelet transform, whatever you have conventional, that has fixed mother wavelet and number of levels, like every time you are downsampling by 2. But these days, such wavelet transforms are coming where you can have, even you can design mother wavelet according to your data. You can change the number of levels. You can change the decimation, upsampling, all based on the parameter. That is known as flexible analytic wavelet transform. So in that actually analytic form, they use initial 2 subbands, low frequency, high frequency. They use 3 subbands, low and high frequency, positive frequency, negative frequency. So when we have used Fourier Bessel series expansion, and by doing that actually this only one part only positive part is frequency part is supported, because Fourier Bessel series expansion does not use negative frequency. So due to that, actually, we have suggested flexible time frequency coverage wavelet transform design using Fourier Bessel series extension. So this is a proposed framework for focal and non-focal EEG signal study, and this is for focal epilepsy. And here FBSC based flexible time frequency wavelet transform will define. Then we obtain subband signals and extract features. Then least square support vector machine classified, and focal and non-focal EEG signal classified. So this is a proposed actually FBSC based flexible analytic wavelet transform. So by doing this, this flexible analytic wavelet transform can be considered like conventional wavelet transform. Otherwise, every time you have 3 subbands. So then we have designed this flexible analytic wavelet transform like conventional wavelet transform using FBSC concept. And then this is an example, is a signal, and these are the parameters used for the decomposition. And you have simple signals, basic base functions or basic component decomposition, decomposed components using this flexible analytic wavelet transform FBSC domain, and then we use them to extract the features like mixture core entropy and exponential energy are computed. Then LSSM classifier is applied, and we have also studied for this noise case also. And so this is the conclusion of this entire talk. The Fourier Bessel series expansion technique together with Wigner-Wheel distribution provides constant-free time frequency representation of non-string signals. And the selection of EEG signal length based on FBSE help us to perform time-varying auto-regressive based modeling of EEG signals. And the FBSE based mean frequency feature computed from enticing mode functions of EEG signals can provide statistically significant difference between epilepsy and seizure-free EEG signals. And FBDESA method provides analysis of multi-component AMFM signals and speech signals with low error. And high-resolution time-frequency analysis of non-string signals can be obtained based on the Fourier Bessel series expansion-based empirical wavelet transform. FBSE-based incomes are used for epileptical identification of entropicus. These all methods, they are studied only for one kind of disease, one kind of data. You can try this or other data like emotions. Nobody has studied FBSE based on for emotion identification, for depression. There are many other problems can be tried. FBSE based flexible time frequency coverage wavelet transform provides improved classification of focal EEG signals. And these are the actually references from our group for this presented work. Please go through them to understand them. In like this order work, this was actually 93. And this was actually paper, starting paper, and nobody cited it. And to time, the first person here they started it extended. So these are some papers on this. We'll share slides. Questions, please. Like basis functions. Similarly, nature has actually developed some fruits also for the different parts of the body. Like the similar structure of the body parts, similar to the structure of the food. Like if you want your good heart, and what we should eat. you want to have good heart, healthy heart, then what we should eat? Chocolate. Yes. Yeah. So actually, yeah, we should eat tomato. So if you cut tomato, then it has 4 chambers. So like heart is similar to tomato. You have the good heart, then you should eat tomato. And if you want to have good eyes, then you should eat carrot. Carrot, you cut carrot, it looks like eye. If you want to have good kidney, kidney beans, kidney beans. If you want to have good brain, akroat. You break akroat, it looks like that.
By using the support of here for the some type of the non-sexual biological signals. You know the lower that or the plan perspective for the similarly for the unknown frequency of the I mean on the signal, you don't know the frequency of they're able to implement the order, they're able to generate the position instantly based on the present input and previous output. Here, speaking about the position generation, in the standard signal parameter, we can develop the
Yeah, it's fine. Actually, suppose your signal is non-stationary, like biological signal, then every time, for example, in this interval, you have a different low frequency, high frequency, and pass band. In other segments, changing with time. It will be different. So that adaptively, you have to estimate them.
Sure, we know that, for example, changes for 0.5 hertz to 100 hertz.
So,
We can eliminate the output signal below 0.5 hertz or above 100 signal by implementing
Yeah.
If the signal is in between the 0.5 hertz to 100 hertz, we will choose adaptive filter as the position instantly by referring the present input and the previous output. So similarly,
no, that is what is the present input output is biomedical.
Actually, the fixed signal value instantly. I mean, previously we can generate the position and we can implement it.
Oh.
It's a known value, I'm saying. Known values. If it is unknown value, for example,
Yeah, this is what is reference is not known.
yes, by that time, you have to apply that special implementation like that position instant. It is completely based on the present input and the previous output. So this is the concept by that the very beginning stage the Fourier series vessel period that coefficients which are playing the major role in that. How do we generate that using the same way things?
Yeah.
Or that same equation itself would be able to generate the coefficient.
Yeah. Actually, it's like in case of Fourier, we design basis functions from our side. The sinusoidal functions, we generate them from our side, and then we whatever signal is there, then we actually determine like integration, that is like inner product. So we measure the similarity between the signal and that particular basis function. So like you have designed, for example, 100 these sinusoidals. So each sinusoidal you will take and you will measure the similarity using that formula, that analysis I have mentioned. From that, and if its value is high, then we say that this frequency is a major frequency of the signal. So similar way, for example, its value is 0. This means that basis function, sinusoidal function that you have designed, that is not existing in the signal because its value is 0. So basis functions also we determine the roots by using Rooter-Epson method, and for each root we design the basis function, this Bessel function. So for example, you have 100 roots. So 100 Bessel basis functions will be there, and low root, like there is a frequency and order relation. So low order means low frequency, high order means high frequency, and that actually will pick up one basis function, and you measure the similarity with the signal, and that particular coefficient, that order is becoming higher, then we say this is the significant basis functions of the signal. So there are two kind of actually directions of signal processing. In one way, we design basis function from our side. Other way, now 1998 is Hilbert Wang concept, this empirical mode decomposition that is proposed by the Wang and others. They say don't need to design basis function. You extract basis functions from the signal itself. So that is adaptive algorithm, iterative algorithms, and they apply recursive manner, and they obtain all possible basis functions from the signal. So this first part is what we are talking, that is like prepaid mobile. Second one is like postpaid mobile. So first you decompose, then you say this is the basis function. In that, first we are designing basis function, then we are representing in terms of that. First we have signal, then we have basis function. In both cases, people are trying to get AM/FM kind of basis function, amplitude and frequency modulated. So that is actually one of the very useful model for non-statistics, where amplitude is changing, frequency. So like voice, amplitude is changing. When you speak, due to the lip movements, amplitude is changing. Vocal tract, frequency change. So it's like AM/FM component. It makes sense. Everywhere this frequency and amplitude is changing. You are looking signal at x-axis, y-axis, then it nicely can be interpreted. That is actually a very good question, because you don't want anybody depressed. Like his question is how to introduce depression in the subject. That is actually not ethical. Everybody should be happy, nice, enjoying life. And for research, the question is how to make someone depressed. That is not allowed. So we actually believe on doctors based on the symptoms. Doctor realize, or otherwise whatever subject is saying, he or she is feeling depression, that we consider. So there is no way. There are many ways to depress people, but for research purpose we should not do. So there is no known case like there is a depression.
Different level of frequency. So, to capture, to capture, we should have to fix the sampling rate of catching the signal. Is it possible to capture the signal?
Yeah, generally like even biopec, the sampling rate is 1000 hertz.
Yes.
So according to Niagara state, it should be more than two times of the highest frequency present in the data. So gamma rhythm the highest. So around 200, 250 should be there. Like it is that is sufficient to characterize all rhythms. All rhythms. So if you are taking care of the highest rhythm, then it is taken care for all rhythms.
Maximum. So,
But if you take more number of samples, then actually this is also very good. You don't want to take more number of samples because this is not good for patient also, and this is not good for method also because it will take more time to implement. You want to have real-time implementation for healthcare. Healthcare, this method should work in real time with fast. Everything, whatever this actually everybody wants to detect in the early stage. And many diseases are not known, like epilepsy. Epilepsy, there is no reason known why it comes. Still, we don't know. But if you see Shastras, our Shastra, they say this is due to your karmas of previous life. Yeah, that is what we have. We have good laboratory in IIT Indore, where we record, even we can detect your emotion also based on the real time. Yeah, but this is actually we have recorded from our institute. So ethical committee permitted to for us only, but I think we can take permission for some processing is required. But anytime you are most welcome to come there, and your students can come, you come there, all record the signal, then no problem. Yeah, we have like Hare Krishna chanting Mahamantra, we have seen the rhythms, alpha, theta, delta, beta, gamma, and where alpha rhythms energy increase. So many actually write mail for this database, but when I ask should, they say was no, this publicly there. Publicly many databases are there. You are talking about Indian databases or this publicly or our private? So there are many databases. This is a Bonn University database for this epilepsy. Bern Barcelona database is for the focal epilepsy. That is publicly available. CH PUNet database, CHB MIT database there for children epilepsy. And no, that is for seizures. It's a very huge database for children epilepsy. That actually one of my students, I was with Aarti and Ravi. She has done some work for NIT Raipur. I was also yeah, she's so publicly available databases are already there, and you may like take any of the method. They all methods, no method is studied. And if you need MATLAB code, we'll be happy to provide you MATLAB code. Then you can try any of the method for that database. Data for this database is publicly available. The we have our own database also emotions. We are recording our own database. Hmm. These biomedical signals are very helpful for emotions. For this speech, many actually the people are smart in speaking, but they have different kind of emotion that is not revealing from the speech signal. Even the space also can be modified. Everywhere. So now we are making our database. Now I am now professor, so I am doing all this kind of work, developing database. Or I'm not doing research work. Yeah, now our brain is different, foreigners' brain is different, our heart is different, their heart is different. Our situations are also different. One of the newspaper that actually after marriage, second day, that person is not identifying his wife. And he asked his mother, who is she? Mother is saying, she is your wife. Because one day before, the beauty parlor people change their face. So emotions actually, even face recognition also face, it can be modified. So this bio, nobody can change your brain. No beauty parlor can go inside and do something there. Yeah, please. Tomorrow we will see this for medical imaging, how to two-dimensional Fourier Bessel series expansion, and then actually we'll be happy to provide you a medical report. One group that is Dr. Rajesh Kumar Tripathi, his students got a lot of interest in this. Now they are making publicly available codes. He has recently this year developed full automated method. So he has got good students and they are doing very well in this. This is new direction. Nobody has done. This is only like you'll find very less work is done, a lot of opportunities. And when I was at IIT Kanpur, my supervisor says you can do a lot of work on this area. This is nobody has done. So I started, and many of my friends used to say, nobody has done. Why you are doing? There is some problem. So there are two ways of looking at it. And today I have seen what my supervisor was saying. It was correct. Many of my friends are saying, why you are not using Wavelet? And nobody has used Fourier Bessel. That is why something is there, something is wrong. You are not understanding. And now I have understood, and I am in the right direction. So take this, and a lot of actually, opportunity, lot of work can be done. Video analysis can be done. Nobody has tried video. This depression, all these things. Bessel domain, whatever Fourier people have done, that is like adaptive filtering concept that you are determining coefficients, but we can use also Fourier Bessel adaptively to change with different time with the reference. Lot of directions are there. Yeah. Uh, I went to Freie University, visiting professor last year, Germany, Freie University, Berlin. HSS department, they are using signal processing, time frequency represent. They go to Aachen University to learn time frequency analysis. I was there for 2-3 months. I told them, why you are going Aachen? I am here. I've written one book on time frequency analysis that actually tomorrow I will say it took me more than 10 years to write that book. So it is the first book from India in time frequency. Just I was having interest, so and you can go through that also. Hmm? Yeah, yeah. Hmm. Yeah, handwriting difficulty. Yeah, actually, one of my student I see a paper. She's doing like a forgery signature. When you have signature, then each signal different. When you are making forgery signature, fake signature, then signal different. So when you have difficulty in writing, that also actually have different load on the brain. Different rhythms will be there. Based on the rhythm, you can detect it. So like even the person they have Alzheimer. Alzheimer people, things are very slow. Even if you ask them to write A, they will write this, and nicely easy signal can be. So this actually we are planning to now. This is one writing. Other one is actually visual cognition. This is new direction is coming in brain-computer interfacing. That is MIT they started, and the Germany, that group that I visited, that one. Third one is our lab. So now we have brain-computer interfacing right now only two. One is based on the wrist movement. So like four left, right, up, down. There are four combinations. Based on that, you can control anything. Other one is based on your speech, vowels A, E, I, O, U. Third one is now based on your visual. So now you can see at time many people. And some people, like writing is one difficulty. Some people have difficulty in looking also. And they see people in different. One of my friend, actually, he lost his glasses in the sea at Rameswaram. We were having bath in the sea together, and he lost his glasses in the sea. When we came outside, for him, Tamil, English, all are looking same. So vision now, his easy signal will be different. He's saying it is, I am saying it is in English, he saying it in Telugu, Tamil, because he not able to characterizing the characters. So difficulty is there, visual, hand, this all are. The three important concepts when you walk down, these people are designing robot, and they want to have like human kind of robot. So human actually integrates three inputs to maintain the balance. One is vision, that actually you should be able to see properly, then only you can walk nicely. Other one is vestibular, you should be able to listen properly, then only you can walk down. Third one is proprioception, like this Jode. They should actually able to understand flexibility. Then only you can walk down. So three inputs they actually in robot people are trying to. There is a nice system. Even people at how it is happening, nobody knows. So many things in human body. And after some time, you don't have balance problems. So many good things in life. When people become old, they go to hospital, then they realize. Yeah, the time for actually lunch. We should have lunch like we are the richest person in the world. And we should have dinner like we are the poorest person in the world. Thank you very much. Thank you.